Okay, so our last subtopic in this concluding lecture on graph is about span trees. Let us define what it means. Let G be a simple graph. By the way, spanning trees are mainly about simple graphs or undirected graphs, not directed graph. So let G be a simple, connected, undirected graph. A spanning tree of G is a free tree. A free tree means a tree with no specific root, but it's a tree in the sense that there are no cycles within the graph. So it's a free tree whose number of edges is number of vertices minus 1 that connects all the vertices of the graph. So essentially is a version of that graph that has the fewest possible edges, fewest possible number of edges that will still connect all the edges. Obviously, that type of graph will have one less edge compared to the number of vertices. So for example, if you have 2 vertices, then we only need 1 edge to connect them. If you have 3 vertices, we only need 2 edges to connect them, and so on. This is the idea. So in a spanning tree, the number of edges, we try to make them as smaller as possible, and the smallest we can have is the number of vertices minus 1. Here is a more formal definition. So a spanning tree for a graph G, which has V and E as its set of vertices and set of edges, is a graph T. We call it T because it's actually a tree, okay, which consists of V prime, E prime. So a different set of vertices, V prime, and a different set of edges, E prime, with the following properties. Okay, 1, the 2 vertices, the 2 set of vertices are actually equal. So to get a spanning tree from G, we're not going to remove any vertex. It's the same vertices from G. Okay. 2, the graph is connected. So the tree we're going to get is still connected. We started with a connected graph, and still we end up with a connected graph. And finally, the graph has no cycles. So any edge that will create a cycle has to be removed from the graph. If you have that, then you are set to have a spanning tree for the graph. How do we get a spanning tree from a graph? Basically, any traversal of a connected, undirected graph will visit all the vertices in that graph. Now, if you take the set of edges which were actually followed during the traversal, you will have a spanning tree. Okay, for example, let us consider this graph. Okay, what will be the spanning tree that you get if you do breadth first traversal of that graph? But as we recall, breadth first traversal, when you visit a vertex, then you have to visit all its adjacent vertices before you go to the children. So suppose we start a traversal from B. Okay, the vertices adjacent to B are A, so we're going to visit A first. So you're going to draw the edge that you followed in your resulting graph. Then we're going to visit C, so draw an edge from B to C. And we're going to also go to E. These are the edges adjacent to B. So draw a vertex there as well. Okay. Now if you go to A, we cannot go anywhere. E, we cannot go anywhere. But if you go to E, it has two adjacent vertices, D and F. That is the way we're going to do this traversal following breadth first. And this is the resulting graph that you get, and this is actually a spanning tree. A spanning tree simply means the same graph but removing all edges that will create a cycle. You see here there's a cycle. A, B, C is a cycle. So the breadth first traversal allows us to eliminate this edge. So now there is no cycle. Similarly here there is a cycle E, D, F. But the breadth first traversal allows us to remove this edge. Okay. Now if you count the number of edges in this resulting graph, there will be one less than the number of vertices. Okay, we have 6 vertices, A, B, C, D, E, F. How about the number of edges? 1, 2, 3, 4, 5. So this is always the case. In a spanning tree, the number of edges is one less than the number of vertices. Okay, let's see another spanning tree that we're gonna get if we do depth first traversal starting from vertex B. Okay. Again, this time remember in depth first, when we visit a vertex, we have to keep going deep. We don't go back to the original vertex unless we get stuck. So here, when we visit B, we go to A, and then we go to C. So you can see the edges we followed. So now we are stuck. So we backtrack to A, we backtrack to B, and then go to E. Okay, so that's how we got this edge. And then from E, the one that is alphabetically first is D. So we go to D. Okay, so that's why we have this edge. From D, we can go to F. So, and at that time, we have visited all the vertices. The whole graph is connected, and we obtain another spanning tree. Okay, so if you do any traversal and take note of the edges that you actually followed, you will have a spanning tree for your graph. Okay. But actually we are interested more in graphs that have weights in its edges. Okay, so here it says for an edge-weighted connected undirected graph G, the total cost of G is the sum of all the weights on its edges. Okay, now we want to try and reduce that cost by computing what is called minimum spanning tree. So a minimum spanning tree for a graph G is a spanning tree for G that has the least total cost. Okay. For example, consider this complete graph. If you remember the definition of complete graph, from any vertex, we can go to any vertex directly. So suppose we have this graph where the edges have weights as listed here. What is the minimum spanning tree for this graph? Okay, now because this graph is complete, actually there are many ways we can connect the graph and try to avoid the cycle. In other words, there are many spanning trees, a total of 16 of them. Okay, so the complete graph on the right has 16 spanning trees. Here are some examples of them. Okay, this is one. Obviously, all the 4 vertices are connected. We only need 3 edges, by the way. Even though here there are 1, 2, 3, 4, 5, 6 edges, we only need 3 to form a spanning tree. To have the graph connected without cycles. So this is one, this is another, this is another, this is another. Okay, just 3 edges. And this is also another. The question is, which of these spanning trees will give you the minimum cost? Okay, Okay, for example, the cost of this one is 8 plus 4, which is 12, plus 1, 13. The cost of this one is 8 plus 3, which is 11, plus 1, 12, and so on. So out of all the 16 minimum spanning trees for this graph, which are the minimum? Okay, so this is the answer. Say the graph actually has 2 minimum spanning trees. Each one will cost only 6. That's a big difference compared to this that is costing for 13. Okay, and these are the two that are minimum. So even the minimum doesn't have to be unique. I hope you can notice from this example. Okay, the cost of this graph is simply 3 plus 2 plus 1, which is 6. Similarly here. Okay, so that is what we are interested in finding in the rest of this lecture. Can we have an algorithm that will tell us the minimum spanning tree for a given graph? What is the minimum spanning tree? Is there a systematic way of doing it? We're going to explore 2 different algorithms. One is called Prim's algorithm, named after the guy, of course, who found the algorithm. And the other one is called Koskas algorithm. So we start with the Prim's algorithm for finding minimum spanning tree. Prim's algorithm finds a minimum cost spanning tree by selecting edges from the graph one by one as follows. It starts with a tree T consisting of only the starting vertex. Okay, so it's trying to create a new graph out of the given graph by first considering only the starting vertex. Okay, then it finds and adds the shortest edge connecting the current T to the rest of the graph. I mean, which edge will connect the current tree to the rest of the graph with minimum weight? It will add that, and then find the next one, and so on until it connects the whole vertices. Okay, so the process is repeated until all vertices are added to T. Okay, here is the algorithm in more detail. So let T be a tree consisting of only the starting vertex X. Now repeat. While T has fewer than n vertices, because remember the spanning tree must have the same number of vertices as the original graph. So while that is not the case, find the smallest edge connecting T to the rest of the graph. The rest of the graph is G minus T. Add that edge to T and repeat the process. Okay, so this is basically what Prim's algorithm is. It's very simple, and what is even more interesting is that actually we can implement this algorithm using the same strategy and table that we use for Koskas algorithm. Okay, that's what we are saying here, that Prim's algorithm can be traced in the same manner as Koskas algorithm for finding the shortest path, which we studied in the last lecture. The only difference is that instead of accumulating the cost from the source vertex or the starting vertex, we only consider the cost of the current edge, okay, from the current active vertex to its adjacent vertices. Okay, we will see this in detail in the next slide or next set of slides. So in the next set of slides, we shall trace the execution of Prim's algorithm on the following graph, starting from vertex B. This is one particular difference between Prim's algorithm that we are studying now and Koskas algorithm that we're going to study next. In Prim's, you will have to be told where to start, so you will be given a starting vertex. But Koskas doesn't need a starting vertex, as we shall see. Okay, so here it says trace the execution of Prim's algorithm for the following graph starting from vertex B. By the way, it really doesn't matter which vertex you start with. You normally will end up with the same result. Okay, as we shall see. So we're going to use, as I said, the same table as we did for Koskas algorithm. We list all the vertices in one column, and since there are 6 vertices, we're going to do 6 iterations, and each iteration we will finalize one vertex and identify its predecessor. Okay, so very much similar. The only difference is how we compute the value of reaching the next vertex. Instead of always starting from the source vertex and add them all until we reach the new vertex, no. For example, if we are at C here, we don't consider B, A, and AC. Just what is the age, what is the weight of the age from C to E. Okay, that's the only difference, as it will become clearer as we solve the example. So let's start. Initially, of course, as we did with Koskas, the cost of the starting vertex will be set at 0, and all the others will be infinity. Okay, so then we start the process. The process simply involved 4 things. Finalizing the vertex with the minimal cost. This is 1. 2. Identifying its predecessor, if there is any. The first time, of course, there is no predecessor. Okay. 3. Making that vertex to be your next active vertex. And finally, positioning yourself at that active vertex and see where else can you reach. Okay, so while you are doing that, you look at the cost. If it is smaller than the previous cost, you will update with the new cost. Otherwise, you just accept the previous one. So these are the steps we're going to be following. Okay, so first step, obviously 0 is the smallest of this, so we're going to finalize vertex B. There is no other way of reaching B that is less than 0. Okay, so the next step therefore is to finalize the B with this value of 0. Okay, finalizing means disabling, if you like, the remaining cells for this row of B, because the value is not going to change. This is the first part of the 4 things that we are supposed to do in the iteration. The next is to identify the predecessor. Obviously for B there is no predecessor, since that is our starting point. Okay, and step 3 is to make B to be our next active vertex. Okay, so now you position yourself at B and ask where can you go from B. Obviously you can reach A with a cost of 13, and you can reach C with a cost of 15. Okay, the rest of the vertices you cannot reach. Therefore, as we did in Koskas algorithm, you simply copy the previous values, in this case still infinity. So this completes our iteration number 1. We repeat the same 4 steps in the next iteration. In other words, identify first out of this which is the minimum. Obviously 13 is the minimum, So mark it as minimum and finalize it. What will be the predecessor? The predecessor is B. You can see we came to A with the cost of 13 coming from B. Okay, usually you can look up and see it at the top. So B is the predecessor. And we now make this vertex that we have just finalized, vertex A, make it to be our next active vertex. Now position yourself at A and ask again, where can you reach? Obviously, where can you reach among those that you have not yet finalized? We have already finalized B, so you don't go back to B. And therefore, the two vertices you can reach from A are C with a cost of 8 and D with a cost of 1. Now, this is the fundamental difference between this Prim's algorithm and Dijkstra's. In Dijkstra's, if you recall, we were trying to find the cost, the total cost from a given source, in this case B, until each vertex. So in that case, we were adding the cost that we reach A with, which was 13, plus the age between A to C, for example, which is 8. So if it were Dijkstra, we will say 13 plus 8, which is 21. But no, in Prims, we are not interested in the cost from the source. We are just interested in finding the age that has the minimal value in terms of its weight. All right, so just consider the cost of the age, which in this case is 8. So we can reach from A to C with a cost of 8. So update that. Obviously 8 is smaller than 15, that's why we are updating. Of course, if you get a cost that is more than your previous value, you're going to reject it. Okay, how about from A to D? It costs only 1. Clearly 1 is better than infinity, so you're going to accept the 1. Okay, now you still cannot reach E and F. Therefore, just copy the previous values from the last iteration in order to complete the present iteration. Okay, identify the smallest among these values. Obviously 1 is the smallest, the cost of reaching D. Okay, so 1 is going to be, the vertex D is going to be finalized. You will never be able to reach D with a cost less than 1. So finalize it, identify the predecessor as A, because actually it was from A that we reached D to get this cost of 1. And so we identify the predecessor as A, and then make it to be your next active vertex. So D is going to be our next active vertex. Repeat the same question. From D, where can you reach? From those vertices that are not yet finalized. We have not yet finalized C, so we can reach C from D. And you can see it will give us an even smaller cost. So it was 15, then 8, and now 5. So we're going to accept that. We can reach E for the first time because E was infinity. We can reach it with a cost of 4. So accept the 4. And finally, we can reach F with a cost of 5. Again, for the first time. So accept it because 5 is smaller than infinity. And that completes iteration number 3. To start the next one, you have to find the minimum among this, which is obviously 4. 5, 4, 5. The smallest is 4. Okay, so we're going to finalize 4. Okay, or rather, we're going to finalize E with a cost of 4. There is no better way of reaching E than 4. Okay, what is the predecessor? The predecessor is D. Okay, because you see we reach this E from D with this cost of 4. So the predecessor is D. And then you make it to be your next active vertex. So E is the next active vertex, and we're going to position ourselves at E and ask where can we reach from E. Obviously you can reach C. C is still not finalized, and incredibly we still have another smaller value. See, the value changes from 15 to 8 to 5 and now 3. Okay, so we're going to accept the new value because it's smaller. Alright, we can also reach F with a smaller value. The previous value was 5, so we're going to accept the new value, and those are the only two vertices left anyway. C and F are the only ones we are yet to finalize. So among 3 and 2, which is the smallest? 2 is obviously the smallest. So we're going to finalize vertex F with a cost of 2, okay, with the predecessor being E. So the predecessor is E. And therefore, we're going to make F, the one we just finalized, to be our next active vertex. Now from F, unfortunately we cannot reach C, and that is the only vertex we have not yet finalized. So nothing we can do other than just copying the previous value. So copy the previous value from the last iteration to complete the current iteration. Now there is only one value in this column that is yet to be considered. Therefore finalize it, accept it as the final value of reaching C, finalize it. The predecessor here, you have to be careful. The 3, we didn't get it from F, we got it from E. So the predecessor is E. Okay, yeah. So again, we position ourselves at C, but this time you will see that there is no vertex to consider. We have finished, and therefore the algorithm will terminate. All right, so this is the tracing of the algorithm, but now we have to compute our minimum cost spanning tree. How do we go about it? Very similar to the way we did with Dishcraft. First of all, start with a graph that contains all the vertices, no edge yet. Okay, then be following from the predecessor to the vertex to draw an edge. But there is a big difference with Dishcraft. Here the cost is simply the weight of the edge, BA. Is not the cost of reaching from the source to the particular vertex. No, it's simply the weight of the edge. So we're going to draw an edge BA with a cost of 13. Okay, BA, because the table here tells us there is an edge from predecessor to the vertex. BA with a cost of 13. 13 is one of the edges we accepted, so there is a BA. Okay, next is there is an edge AC with a cost of 3. Okay, sorry, there is an edge EC rather, EC, this is not A. EC is here. So from E to C with a cost of 3, we have accepted it. Okay, then from A to D with a cost of 1. So this edge is going to be accepted. Notice so far no cycles. Okay, so this is accepted. Next, there is an edge DE with a cost of 4. DE. Okay, so DE is accepted with a cost of 4. Okay, notice the same weight as in the original graph, because this time we are just looking at the weight of the edges. Okay, and finally there is an edge EF with a cost of 2. Okay, with a cost of 2. So this is your minimum cost spanning tree. What is the minimum cost? Just add these values and you get the minimum cost. So the minimum cost is 13 plus 1 plus 3 plus 4 plus 2. If you add them up, you will have 23. This is how to find the minimum cost spanning tree for a graph using Prim's algorithm. We use the same table, same idea as in Koskas algorithm. The only difference is we will not be accumulating the cost from the source. Just be considering the weight of the edges that you are considering. All right. The second algorithm that we can use to find minimum cost spanning tree is probably even easier. It's called Koskas Algorithm. And as I said, the algorithm was devised by the guy named Koskas. Alright, so another popular algorithm for finding minimum spanning tree or minimum cost spanning tree was devised by Joseph Koskas, that is the full name. In this method, edges are first sorted by weights. So this is the first step in this algorithm. Sort your edges according to their weights. And then each edge in the sorted sequence is accepted or rejected. Well, it's checked to see if it will be considered, if it will be accepted as part of the tree or not. It will be accepted if it doesn't create a cycle. All right, it is not added to the tree. It is added actually to the tree if no cycle arises after its inclusion. So a very simple algorithm. Sort your edges according to their weights and then follow them one by one, adding them to the spanning tree as long as the edge that you are adding doesn't create a cycle. This is a simplified version of the algorithm. Okay, it starts with an empty tree, no initial vertex. This is the difference, as I explained earlier, with the prims. In prims, you have to be given the starting vertex. Here, no starting vertex. You start with an empty tree. Okay, you sort your edges. So edges here become sequence of edges of the graph, which are sorted by weights. And then you start a loop from 1 to the number of edges, as long as I is less than the number of edges, and the tree has less than number of vertices minus 1 edges. Because once we reach number of vertices minus 1, we should stop. We cannot, the graph will have been connected at that time. All right. So what do we do in each iteration? If we check if the edge EI from the edges that are already sorted, if the next edge will not form a cycle if it is added to your tree, then add it to the tree. All right, so again, I'm going to show you with an animation an example that clearly demonstrates how this example works. So we're going to do it with this graph, which is having even more edges than the first example that we saw. So tracing of the execution of Koskas algorithm using this graph. So here what we do is we use a table, but not the same table as we use in Prims or Koskas. This table has 3 or 4 columns. I say 3 because the last row here, 3 or 4 rows. And I say 4 because the last row here really is not important. It's just telling us in what order we accepted the edges. But the 3 main important rows are the rows where you list your edges, their weights, and the status, whether we accepted the edge to be added in the tree or not. Okay. Now the first thing, as the algorithm says, is to sort your ages according to their weights. Now, looking at this graph, you can see that the smallest weight you can find is 2. And there are 2 ages with 2, AD and EG. Okay, so you're gonna have them first in your sorted list. Okay, so as you can see here, I have put the weight of 2 twice, and they correspond to ages AD and EG. Please notice how we name the ages. As we know, in simple graph, the age can be regarded as AD or DE, but we prefer to name them alphabetically. So the first letter that appear first alphabetically, we should have it first in the name of the age. So we're going to call this age AD, not DA. Similarly, this age is called AG and not GE. The second point to note is when you are sorting them, if they have the same weights, so which one will appear first based on the name of the age? If obviously AD will appear first before EG because A becomes before E. So this is also important because it will determine which of these twos do we accept. If you don't follow this, you may get a different tree than another student, and we want all the trees that everybody will get to be unique. So the simple rule to use is when you are naming your ages, name them from the smaller letter to the bigger letter. This is one. Rule number 2, if the ages have the same weight, put them in the sorted list starting with the one with the smaller letter. Right, I hope this is clear. The next smaller values in terms of the ages, the weight of the ages in this graph are trees. And we have 2 trees also. This is a tree and this is a tree. What are the name of the ages? A, B, and F, G. So we're going to put the 2 trees and the 2 ages in our graph. Again, notice the ordering that we put them. A, B first before F, G, because A appears before F. Okay. What is the next set of values? In the order of the weights will be 4. And again, there are 2 ages with 4. This one and this one. Which one will come first? Obviously, the one that starts with A. So AE followed by DF. Okay, so this is what we have. 2 values of 4s, and the corresponding ages are AE and DF. What is the next value bigger than all of this? Is 5. This time there's only one 5. And the age is called AF, not FE, AEF rather. Okay, so we're gonna put 5, and the name of the age is EF. Next is we have at age 6. Okay, so we add it, and the name of the age is DE. Next we have 7, only one 7, and the name of the age is BE. Okay, after 7, the next value actually is 10. This is the next bigger value, so we're gonna put 10, and the age is AC. Then we have 12, and the age is CD. And finally we have 15, and the age is CF. Okay, now notice if you are doing this, assuming you are not giving a table, that you have to draw the table yourself, how do you know how many columns are you going to have? Simply just count the ages. If you count this, you will see that there are 13 edges. So just create a table of 14 columns. The first column will be used to put these levels, age, weight, and status, and then the rest will be used to put the ages, each age along with its weight. Okay, so this is the first step of the algorithm, the Koskas algorithm. The first step is sort the ages according to their weights. So we have done that. We have sorted the ages of this graph according to their weights. Those with 2s, then 3, then 4, then 5, and so on. Now we're going to start the loop. Now, again, before the loop, draw all your vertices, because as we know in spanning tree, the vertices don't change. We will have the same vertices. It is the ages that we will want to know. Are we going to accept this age or not? Now, the Koskas algorithm simply says, take the age that has the smallest weight and add it to the graph as long as it will not create a cycle. So obviously the smallest age, well, there are two smallest, AD and EG, but we're going to take AD first because it is the one that appears alphabetically first. So we're going to try and add AD. Obviously, being the only age, it will not create any cycle. So we're going to accept it. So as you see, this column is simply to be used to indicate whether you accepted an age or not. Okay, this row of status is the status of whether the age has been accepted in the spanning tree or not. Okay, so a tick means it has been accepted. Okay, the next age is EG. Okay, with a cost of 2. So again, clearly we will accept this age because it doesn't create any cycle. Next age is AB with a cost of 3. Again, adding it doesn't create any cycle, so we're going to accept it. Next age is FG, which is again also going to be accepted because so far there are no cycles in the graph. Next age is AE, which we shall again accept because no cycle will be created as a result of adding it. All right, but watch what will happen because next is DF. Now clearly adding DF is going to create a cycle. Therefore, we're going to reject DF. So DF will be thrown away. And here in the column for status, we marked a cross that age DF was not accepted because adding it will create a cycle. Okay. Next is age EF. Now again, you can see EF, adding it will create a cycle. So EF is equally going to be rejected. Throw it away because it will create a cycle and the status for it is rejected. Next among the list of sorted ages is DE with a cost of 6. Again, clearly adding DE will create a cycle. Okay, so the cycle is going to be, the age is going to be rejected, so it's going to be thrown away. Next is BE. BE is also creating a cycle. As you can see here, this is a closed cycle. Closed cycles are not allowed in a spanning tree, so it's going to be rejected. Okay, our graph is still not connected, so we still have one vertex, so we have to continue. The next age, however, is going to complete it. Okay, the next age is AC. Notice that even though the cost of AC is 10, more than the cost of all these ages that we rejected, we have to add it because we need to connect our graph with C. All right, so we're going to accept this edge, because clearly adding it will not create a cycle. Now at this point, our loop is going to stop. We don't have to worry about the remaining edges, basically CD and D and CF. Because what? Because our graph is now connected. All vertices are connected. So at this point, the loop will actually terminate without even considering HCD and CF. Okay, so this is the final minimum spanning tree you're going to get. The last row here, as I mentioned at the beginning, is not necessary. If you are doing it in an exam, you don't have to keep this row actually. It is only telling us the order of accepting the edges, okay, which is basically the order of the edges because they are already sorted. So the ordering is 1, 2, 3, 4, 5, 6, as you can see here. So what is the minimum cost? Just add the weight of the edges that you have accepted. 2 plus 2 plus 3 plus 3 plus 1, 4 plus 1, 10. If you add all, you're going to get 24. So this is the minimum cost for this graph using Koskas algorithm. Maybe as an exercise, you can try to see if you will get the same result using prims. Usually the result will be the same. The last example here is from the book, but the book is trying to accept the edges mentally rather than using a table. I suggest you use a table. So I will leave it to you again as another exercise. Try to solve this example using the table as we have done in the last slide, and see if you can end up with this graph. This is the minimum cost spanning tree for this graph. And this brings us to the end of this second part of the lecture on graphs. Thank you very much.